Thank you, as always, to Kyndryl and the Kyndryl Institute with a unique blend of AI-powered consulting built on unmatched service capability. Kyndryl helps leaders harness the power of technology for smarter decisions, faster innovation, and a lasting competitive edge. Also, check out the Kyndryl Institute. The Kyndryl Institute has a plethora of brilliant writing, brilliant thinking, and thought leadership from many of the guests who have been on the show and will be on the show in the future. You can find that at kyndryl.com/institute. Facts change all the time. Smoking has gone from doctor recommended to deadly. Meat used to be good for you, then bad to eat, then good again, and now it's a matter of opinion. The average internet connection is far faster now than it was 10 years ago. The language of science has gone from Latin to German to English and is certain to change again. Humanity has progressed from a population of less than 2 billion to more than 7 billion people in the past 100 years alone. We have gone from being earthbound to having had humans walk on the moon, and we have sent our artifacts beyond the boundaries of the solar system. Chess, checkers, and even Jeopardy have gone from being the domains of human experts to one of computerized mastery. Our world seems to be in constant flux, with our knowledge changing all the time. Even the most informed people can barely keep up. All this change may seem random and overwhelming. Dinosaurs have feathers? When did that happen? But it turns out there is actually order within the shifting noise. This order is regular and systematic, and is one that can be described by science and mathematics. Today's guest offers a guide to the startling notion that our knowledge, even what each of us has in our head, changes in understandable and systematic ways. Knowing how knowledge works can help us make sense of our world. It can allow us to anticipate the shortcomings in what each of us might know and help us to plan for these flaws in our knowledge. Including the flaw, if you didn't notice, that we've gone from 7 billion to 8 billion in the time that our guest wrote the book in 2012. It is a pleasure to welcome the author of The Half-Life of Facts, Samuel Arbesman. Welcome to the show.
Thank you so much. Great to be chatting with you. This is exciting.
Oh man, I have learned so much from this book. We talked about off air that so much has changed since you wrote it, including a lot of the tools that you mentioned in the book, but I found it a magnificent read, very well researched, etc. I'd love you to tell us about your thoughts since you first wrote it. What's changed, what hasn't changed, and that'll set us up for some context for the book.
On the one hand, I think the general rules about how what we know shifts over time, those things are pretty evergreen, kind of perennial truths. In terms of what's changed, actually one fun thing that actually I discovered, I think between the time the book went to press and when it actually published in hardcover, and then we were actually able to change it for paperback, was one of the stories I tell about how errors propagate and how they're eventually rooted out is this well-known story about the iron content in spinach. So there's this well-known story that there was like a typo, and then of course, then people thought that spinach had a lot more iron content than it did, and as a result, that's why Popeye consumed spinach, and this whole story. And people have been writing about this story, I think, since like the early 1980s when someone wrote about this. I included it in the book, and then of course, once the book went to press, I discovered that it turns out this story of how error propagates and then gets rooted out is itself erroneous. It turns out someone has actually done research and shown that no, it was actually some sort of like, I think it turns out that spinach, it wasn't necessarily that much more iron filled. There might have been some sort of mistake in how the science was done or whatever, but it was this weird thing of like the story of error itself was erroneous. And then it took time to actually root that out. And then I was able to modify it for the paperback and then actually mention this in the afterword of the book. But that was just one small example of even when you're trying to understand how knowledge changes, how what we know changes, there's always going to be things that are modified. So there was a professor of mine from graduate school. He once told me this story that he was teaching a course. I think he went in on like a Tuesday, lectured on something. The very next day, he read an article that actually invalidated everything he had taught the day before. So he went in on Thursday or whenever the next day was when he was teaching, and he said, "Remember what I taught you? That's wrong. And if that bothers you, you need to get out of science." And so there's this idea that science, rather than it being just a body of knowledge, which I think is often how we think about science, it's really a rigorous means of querying the world. And so that rigorous means is not going to change. The body of knowledge might change, though. And so there's this understanding that we have to recognize these things are always in draft form. And so whether or not it's the facts in the book itself, which I'm sure have changed even more than I realized, or even just kind of other things that we think about in our textbooks, we have to recognize that kind of thing. I would say one other thing that I will mention in the book is when I was talking about people reproducing scientific experiments and how we don't often get a lot of credit for just recapitulating what other things that other scientists have done and saying that, oh yeah, probably a lot of science is kind of messy and we're not necessarily going to know whether or not those things are correct. Since I wrote the book, I'm actually gratified to see that a lot of people have actually started doing a lot of things around reproducibility and actually repeating experiments to see to what degree certain well-known scientific results are actually true or don't really hold up under scrutiny, and realize, oh yeah, these things were kind of just some fluke or whatever it was. And so people have been doing that. And so I'm actually really gratified to see that my expectation that no one would actually be doing those experiments is wrong. And so
I was literally just reading about Fermat's last theorem in that respect, where people thought it wasn't solvable, and he said he had the solution, but he didn't write it in the margins. And the fact that people assumed it was unsolvable. And I think that was one of the things I really appreciated about the book, was it makes you question what you're looking at or even what you reference. And I do a lot of referencing in my writing, and I was actually thinking about that. Is like, don't ever take for granted the reference that somebody else gives. Go and search it for yourself, especially in this world.
yeah, Fermat's last theorem, he's a mathematician, and then in the margin of one of a text, he basically said, okay, here's this mathematical equation, and he basically posits something about that equation and saying, like, there's no solutions beyond the cubes, or I forget exactly what it was, or the squares. And he's like, oh, but like the margin is too small to contain the proof. And of course, this set off this, like, I guess, multi-century quest to find it. And then eventually it actually was solved. But that proof, it was not, oh, just a little too large to fit in that margin. It was much too large. And so there could be a situation where he probably was wrong about the proof, but at least it goaded mathematicians to actually make a lot of discoveries and do a lot of different bits of work. But more broadly, what you're talking about of like checking references and things like that, it's very common where knowledge gets propagated from like one generation to the next or from one article to the next, and it's not always traced back to its source. And you discover that, oh yeah, things have been, I guess, copied incorrectly or written down wrong, or certainly in the case of like references themselves, not even like the knowledge in the references, you can actually see the way in which incorrect references and like the page numbers are wrong or whatever has actually propagated. And so people have actually looked at this kind of thing as sometimes a rough metric for whether or not people are actually reading the articles. I'm not really sure that's entirely correct, because especially if you're using some bibliographic tool, maybe it has an error in that. And so that being said, though, I think it just kind of is the broader sort of proxy for recognizing that sometimes it's useful to take things based on experts. Sometimes you actually want to chase things down, but recognizing the way in which we should question certain things sometimes. I mean, and I'll say this always with caveats, and of course, everything is full of caveats, but I think a healthy dose of questioning is very important to understand. Certainly as a scientist, are you kind of taking them as a given? Are they worth re-examining? Should you check the references? Should you check other things? Checking out underlying sources? These kinds of things are actually very valuable to really understand and root out error as well.
Particularly, I think, we talk about AI hallucinations, but we do it ourselves. I was thinking recently about an episode that I love the way the dots connect when I read a book like this. I was thinking about an episode we did with Elise Lohan, who wrote a book called On Your Best Behavior. And it's about how women were kind of framed in society, but mostly through literature and going right back to ancient books like the Bible, for example. But when I was reading about, like, say, the transcription error of the spinach story you told us, that I was thinking about how much translation is based on the interpreter who was the scribe who was writing it from maybe generation to generation, or writing it through their own biases. So it always suited the person who was writing the story, whatever they believed in, etc.
No, I love that. And actually, it reminds me, I mean, before we started recording, we were talking about publication, editing process of books and things like that. And that's actually one of the really hard like hard aspects of writing is when you are trying to actually edit your own writing or read it over, there is an assumption of what you thought you wrote versus what you actually wrote. And so there could be very obvious typos that you will just never notice because you have an assumption. And I believe actually in the hardcover version of my book, I made some like very like simple error about like describing something related to like, I don't know, like metric prefixes. And it was one of these things where multiple people read this. And it was not until my grandfather read it over and was like immediately like, oh yeah, this is wrong. And of course, and it was because I had the assumptions of what I thought. But more broadly, right, there's always going to be a mental framework to how you actually assimilate knowledge or assimilate information. And that is going to color all these different kinds of things in terms of how you perceive new facts, how you choose to absorb knowledge or fail to. And there's lots of things around certain cognitive biases, like confirmation bias. Like we tend to go towards things or are drawn to things that reinforce the framework that we already have in our minds, and which makes it that much more difficult to root out errors. And actually, and related to in your introduction, you were talking about with like, since I wrote the book, it went from like having the population of like 7 billion to like now we're well into the 8 billions on Earth. But there's a story, I believe I actually tell it in the book, where someone told me that he was listening, this is years ago, he was listening to a like well-known like hedge fund manager or investor. And he was like, he started his anecdote with, like, as we all know, there are 4 billion people on the planet. And yeah, it might have been a while ago, but there were not 4 billion people on the planet when he was telling that. But it was because he had absorbed that bit of information and then had just maintained it for years and years and years without actually taking the effort to actually mentally update that bit of information.
And I think that's the thing. When you think about stories you hear, for example, I'm into pushing the boundaries of my health, for example. So I'll try new supplements and people will go, oh, creatine, for example, is really bad for you or whatever. And they're basing it on studies that were like 30 years old. And it's probably one of the most studied molecules at the moment, but they don't update the research in their head because, as you say, it's kind of like this frozen moment in time that's sealed into the brain and that's the fact forever. And that's what I love about the book, particularly when the speed of facts being revealed seems to be increasing as well. I thought what we'd do, Sam, was I'll pull out from the book some of the brilliant examples that you give. One of the ones at the moment that just came to mind, and I'll probably jump around the book a little bit, was to your very point there, is if I am in some way incentivized, then my confirmation bias becomes even more enhanced. And I thought about this great battle between these two paleontologists to discover dinosaurs, which was one of your childhood passions as well. But one of the things that it led to was a false dinosaur that I'm sure many of our audience think is still real. I'd love you to take it from there.
Right. I grew up loving dinosaurs when I was a little kid. I feel like many little kids are obsessed with dinosaurs. And certainly in my own like childhood, there were actually a number of dinosaur facts that were changing quite a bit when I was young, of like recognizing that in fact, like many dinosaurs might have actually been warm-blooded instead of cold-blooded. And now we have a much better understanding of that they actually might have had colors and feathers. And like there was all this information that's kind of changing. And of course, that, I mean, even though the picture of dinosaurs now is these like, I don't know, like fearsome chickens, these like colorful fearsome chickens versus these like kind of slow plodding reptilian monsters that are kind of gray green. We often, like whatever we kind of learned when we were younger, we often failed to update. And one of the kind of well-known dinosaurs from my childhood was the Brontosaurus, which was one of these like the giant four-legged dinosaurs that kind of walked around like with the really long necks. And it turns out that, that name just has not actually been an acceptable name for a dinosaur for many, many decades, I think, at this point, where it's actually the Apatosaurus. And it had to do with, I think that, yeah, there was these two paleontologists, Cope and Marsh, if I'm remembering correctly. And it has been a while since I've remembered the story, so you can correct me on certain of the details, but they kind of had this battle of like trying to like discover dinosaur after dinosaur, who could discover more. And it turns out, so the Brontosaurus was actually, I think, a version of a previously discovered dinosaur in this case was the Apatosaurus. And I think it might, not only was it described wrong, or maybe it was like actually a juvenile of the original Apatosaurus, but I believe they even put the wrong head on it, if I'm remembering correctly. And so it was this thing that, like, on the one hand, like, there's this idea that, like, it maybe was just classification or priority of the name or whatever, but it sounds like there actually might have been more in terms of, like, actually what the understanding was of this kind of dinosaur. And I'm sure, yeah, many people are like, oh yeah, Brontosaurus, it sounds good, we'll use that. Apatosaurus maybe is not quite as alliterative, I don't know. But yeah, right, that was an example of one of these dinosaurs that really people might think is a valid dinosaur name, but not really. And we have like example after example of these kinds of things. One classic one is just Pluto. Like, is Pluto a planet? Is not a planet? And of course, it was reclassified in, I think, 2006 as a dwarf planet, and now it actually might even have a different designation. They might have actually even changed that title more. I vaguely remember reading something recently about that. But it was not because, in this case, and Pluto stopped existing. It wasn't like, oh, like it was a planet and then like it blew up and then now it's not a planet. It was more just we learned more things about our own solar system and realized that Pluto was simply one of this larger class of things that were these very large objects beyond the orbit of Neptune. And so it really couldn't fit the designation of planet. But of course, that's not the first time that kind of thing has happened either. When asteroids were first like being discovered, these like the asteroids are these, the entire asteroid belt are these large bodies between Mars and Jupiter. The first few were actually classified as planets. Like I think Ceres is the largest one, and there's some other ones as well. And so in the same way that generations of children learned Pluto was a planet and then had to grapple with that changing knowledge, I include myself in that, that there were also generations, or at least a certain period of time, where children were taught, I think in the 1800s, that there were these other planets, like Ceres and other ones, which were eventually reclassified as asteroids. And so there's just this constant like reclassification, learning new things, and modifying how we actually have to think about the world. And I think for some people, that can be really overwhelming. And I'm sympathetic to that. I think, though, at least from my perspective, it's actually really exciting. It's not to say, oh, like, therefore, because we thought this was true and this now other thing is true, we have to throw everything out. That's not really how science works. It's this like sort of asymptotic approach to the truth. And we can talk more about that. But for me, like that frontier of like where we're learning all these new things, yeah, there's going to be a lot of shifting knowledge, like whether it's like nutrition supplements or whatever kind of changing and people having outdated knowledge. But that means that that's where the most interesting stuff is happening. And so playing at that frontier means you're going to have to update your information. But it's still worthwhile because then you get to play at that frontier of knowledge.
What it tells you as well is the importance of ongoing learning. I think that was one of the things as well that dawns on me and why I love doing the show. And I was complimenting Sam, for those who are watching us on YouTube, on his library behind him. And he says, oh, that's only one of my libraries. And the one thing you learn by doing this is how little you know. That's the big thing. And then on top of that, that the facts keep getting updated. And that means that ongoing learning is a competitive advantage today. I really felt that. But I
Sure.
thought we'd share some of your terms. So you have this term mesofacts or misofacts, and I'd love you to explain that. And then maybe a couple of places where they show up. One of them, for example, and these are just fascinating examples, was that a cytologist is somebody who explores the interior of cells. A famous one once said the diploid chromosome number of 48 in man can now be considered an established fact. Stamp, that's done, never change again. That's one. And then the other one, and this is one you shared about your granddad, was the fact that when he learned about the chemical elements in the periodic table, there was a certain number. Today, there are far more.
The idea behind, the mesofact is that we need to recognize that what we know, like the different kinds of facts or different bits of knowledge, they change at different rates. Now, it certainly feels like right now, like everything is changing more and more rapidly. And so maybe there is some truth to that. But there are different kinds of knowledge that change, and there are certain types that change very rapidly. And so, like, this is not necessarily like a scientific fact, but what the weather is going to be like tomorrow, or what the stock market closed at yesterday. Those kinds of things, you know, that if I memorized what the weather is going to be like tomorrow a month ago, that has little to no bearing on what that's going to happen like now, because I have to recognize, okay, seasons change, information is updating. And so those are things that change very rapidly. And on the other extreme, you have facts that change very slowly or effectively never. And those are the kind of things that you assume you should learn them once, and then you don't have to worry about mentally updating those kinds of things. And so the example would be, I don't know, how many fingers are on the human hand. You learn that fact and you're like, okay, that's a set thing. I don't have to worry about changing. But in between are these misofacts. These are the facts that change on the order of decades or on the order of a human lifetime. And they can include things about the population of the Earth, but they can also include facts about the state of our knowledge, like the number of elements in the periodic table. And this fact, like how many there are, has been changing slowly and steadily and surely. The problem is that we often learn misofacts, these slow changing facts, the same way we learn facts that are ones that never change. And we are not really incentivized to actually update our knowledge. And so we learn about the current state of knowledge of dinosaurs, the current number of elements in the periodic table, without recognizing that these things actually are slowly but surely, steadily shifting over time. And so I think now the periodic table is, I think we're up to 118 elements. Certainly it was far fewer. Yeah, my grandfather, he lived to the age of 99. He learned lots of different things. He was trained as a dentist and actually related to the cytology thing and like the number of chromosomes in a human cell. And so you quoted that cytologist, and of course, that fact is wrong. There are not 48 chromosomes in a human cell. There are 46. But it turns out there was a period of several decades where we were able to actually magnify the cell and actually count the number of chromosomes, but apparently not count it correctly. But it was miscounted, and then it got propagated in textbooks. And my grandfather, he learned medicine during that period. And so he actually learned the wrong number. In addition to learning an outdated number of elements in the periodic table, he actually learned the wrong number of human chromosomes. And I think, yeah, and it wasn't, I think, until the 1950s that bit of it was actually like remeasured or recounted, and they realized, oh, it's actually, there's only 46 instead of 48. But too often, we just don't realize that we need to constantly revisit a lot of these things. Sometimes that is until, I don't know, our kid comes home and says, guess what? Dinosaurs look totally different. And then you're stunned by it, even though, of course, knowledge has been changing slowly and steadily, but we often perceive it in these kind of like staccato jumps. There's kind of almost like a generational overturn of knowledge. And going back to what you were saying with reading and actually constantly having the need for revisiting and learning things constantly, we talk, right, certainly around the time, maybe we don't talk about it as much anymore, but certainly around the time I was writing the book, there was a lot of discussion around computer technology and the internet and whether or not these things are ruining our memory. And maybe that's true, but I actually think the good part, like the upside of that, means that we're constantly forced to revisit knowledge and actually look things up and discover whether or not the things that are half remembered in our minds are actually still true or not. And so I actually think there is something to be said for, it's good to know a lot of facts and use that as a framework for understanding the world, but also you also need to have that like kind of meta fact, which is these things are all subject to revision. Most of the things are actually these misofacts, and they should be revisited. And yeah, I think having that sense of like constantly needing to learn is very important. And actually returning to medicine, I think medicine is one of the fields that has actually done a reasonably good job of inculcating that in medical students and physicians, because they recognize that a huge number of things that they learn are going to become obsolete or outdated within a few years of medical school. Sometimes they're actually told this kind of thing explicitly within medical school. My father, who's a retired dermatologist, he actually told me this story, which I think I mentioned in the beginning of the book, where a professor of his gave a multiple choice exam, and the exam was identical from one year to the next. The actual choices were the same, but one year, one of the choices was correct, and the next year, a different choice was correct. And medicine recognizes that. And there are tools to remain up to date, like there's online tools for these kinds of things. But I think we need to recognize that kind of thing in whatever field we're in. And I think the downside, going back to kind of this generational approach to knowledge, when we are young, we are trained as generalists. We learn a lot of different things about lots of different fields, like geography and the sciences and history and English language and literature. And then as we get older, we specialize and we learn more and more about less and less. And we fail to mentally update any of the things that we learned when we were younger. And so that's why we often then are not confronted with the changing facts until our children maybe learn those kinds of things. And yeah, maybe this is just sort of a paean or a plea or a charge to action of like, yeah, we actually should periodically try to actually revisit these things, because otherwise we're going to be making decisions based on faulty and outdated information.
We did a series with a guy called Mano Kapoor on his book called Productive Failure. And it was for that very reason. It was like the need to update these mental models. But To your point there about the idea of using some technology to be able to upgrade yourself, by that, this idea of cognitive offloading, where maybe you might use a calculator or ChatGPT, is the whole idea there is that actually that allows you to actually connect more dots. He was saying that that's seen as a negative thing, but actually can be a good thing, especially if it's something that's basic and you have mastered already. Then you can go up a level. I thought that was a really interesting connection that I made as a result of doing the show. But there was one thing that you said there I thought was really interesting, was the idea that if you're, say your granddad was a dentist, your dad was a dermatologist, but he used his skills to connect dots in a very unique way. And I'm bringing us here to the idea of using the power of the crowd. And here he actually solved one of the solutions on Innocentive.
Yeah, so
I'd love you to share that
so
story.
Innocentive is this. I actually don't even know if it's still around.
It is actually. They sponsored the show recently.
So Innocentive, it's this crowd-sourced solution platform where the idea behind it is that if you have a problem, some sort of like scientific question or some sort of other technical kind of question, and it might feel insurmountable, there is a decent chance that the crowd, who has access to different kinds of information and different bits of knowledge, could potentially solve that kind of problem. And so, yes, my father, he's a retired dermatologist. He saw a challenge related to finding new ways of diagnosing ALS, the neurodegenerative disease. And one of the things he did was actually look to a book from 1880. I think it might have actually been the first time ALS was actually described. And he noticed this curious fact that I think it mentioned, just kind of in passing, that patients with ALS did not develop bed sores. And so he realized, oh, wait, as someone who's a dermatologist and kind of understands things about skin, that's curious. Maybe it has to do with skin elasticity. And so he developed this hypothesis around actually being able to diagnose, like very early on, ALS by measuring skin elasticity. And eventually, yeah, and it won, I think, one of like the hypothesis tests. I don't remember exactly what it won, but it was one of these things of like being able to kind of combine different bits of knowledge. It's a neurodegenerative disease, but in this case, he was drawing on information from dermatology, from understanding skin. And the truth is, this is the kind of thing that we need more and more, certainly as scientific knowledge and just kind of knowledge more generally becomes larger and larger. There is no way that even decades ago, anyone could hold all of that in their heads. And certainly now it's completely overwhelming. And so we need either individuals from different kind of areas to draw on bits of information that maybe subject matter experts would not otherwise know. Or even going back to your cognitive offloading, we need computational tools to actually allow us to help stitch information together. And so one of the first examples and kind of approaches to do this kind of thing was this information scientist by the name of Don Swanson. He wrote this paper called Undiscovered Public Knowledge, and this is in the mid-1980s. And he basically developed a thought experiment. He said, okay, imagine there's somewhere in the literature that a paper that says A implies B. And there's somewhere else in the literature, maybe in a different subfield, maybe an entirely different field, there's another paper that says B implies C. And so if you combine them together, you would say, oh, actually, maybe A implies C because I can combine them together. But no one human has ever read these things. And so therefore, that knowledge, that underlying information is actually undiscovered, but it's public. And so it's there, but no one actually knows this kind of thing. And so at the time, he was not content leaving it as a thought experiment. And so he used the kind of then cutting edge computer technology, which in this case was, I think, looking for keywords and like a medical database. But he actually found a relation. I think he made a number of different medical discoveries, including one where he found a relationship between like consuming fish oil and helping to reduce like certain issues around like some sort of circulatory disorder. And then I think he ended up publishing in a medical journal, even though he was not a physician. And of course, since then, we've made huge strides in the kinds of computational tools that can be used to actually surface this kind of undiscovered public knowledge. I mentioned several of them in the book, I believe. And of course, since then, now with generative AI and tools that can ingest huge amounts of scientific literature, we can just do more and more. And I think that kind of collaboration between humans who can notice interesting things but also use computational tools to help say, okay, how can I find unexpected collisions between these different ideas, or take these computational tools and say, okay, now I can aim them towards these kinds of things. I think that that human machine partnership is going to become increasingly important to allow us to actually do this sort of combinatorial discovery process.
I think it's really interesting when you read it in different fields. If you read it eclectically, you start to notice patterns with things, and you go, that thing that happens over here is the exact same happens over here. I write a weekly article, and for that reason, I've quoted you many times in recent articles, including the spinach paradox, I call it as well. But it's because you spot these either metaphors or analogies, and you also spot that if you read right back to the early literature, for example, in Disruption in Companies, you find that the Mark Twain quote is very true, that history doesn't repeat, but it rhymes. So you see these templates all the time, and you can see them very clearly. And I think that's one of the things I look forward to with technology now, being able to mass provide this way of thinking for the world, which leads me to this point. And I want to just say to our audience, stay tuned for exponential growth. So I've said at the start, Sam gives us lots of tools to understand. Exponential growth is one. The Moore's law of everything is another one. Many people will be familiar with Moore's law. But I thought about something there, Sam, which is the speed of discovery of everything. And you mentioned, for example, with medicine, is also enabled by the changes in technology. And I thought recently about how, say, for example, you see these true crime documentaries or maybe some type of series on Netflix or whatever platform you watch on, and you see that they have these resurrected cold cases. And it's now because now the technology is available to be able to look at the DNA, and then they're able to solve the crimes, etc. Even identify bodies, for example. And I thought, well, that's the same thing. That same template is what happens with knowledge, because as the technology enhances, our access to the knowledge or our understanding of the knowledge changes.
Right. As we learn more, it's going to affect how we place everything that has come before us kind of in context. And certainly as we develop new technologies, that in turn allows us to understand new things. And I think, right, there is this deep interrelationship between technological advancement and certainly tool development and the growth of our scientific knowledge. And so certainly one simple thing will just be around like measurement. Like as we have gotten better and better tools to measure our surroundings and quantify it, visualize it, all these different kinds of things, we have in turn learned new things. I mean, like certainly the interior of the cell, for example, like that, as we've developed better microscopy techniques, better staining techniques to actually kind of highlight certain things, we've learned a lot about the organelles, like the kind of these things within the cell. But also we've learned, that's kind of at a very small level, but we've also learned things at the level of the globe. As we have gained better and better techniques to visualize our planet with satellite imagery, to measure certain things down to very, very tight precision with like a global positioning system, things like that, we have in turn created a better and better model of our own planet. And of course, you can see this with, there's like weather prediction. As we have more and more weather tools, we've not only been able to predict weather better, but we might actually understand how weather works better. But there's just example after example of like, I don't know, increasingly powerful particle accelerators that has in turn led to new knowledge about fundamental ideas around physics. The idea is that, right, like we think of kind of technological advancement as kind of, oh, this thing of like, oh, we're getting new gadgets or better battery power for our phones or whatever. And yeah, there is a lot of that. But a lot of those things are also deeply connected to our ability to actually understand the world itself. And so you can see that as these technological advancement happen, they move hand in hand with better scientific knowledge. And certainly even with like, as we now have these new AI tools that can in turn allow us to maybe stitch together different domains that we might not otherwise have been able to actually connect together. And so there's a lot of these tightly intertwined marches of technological advancement going hand in hand with scientific advancement.
Which teases up beautifully for exponential growth. And I have this little just excerpt to tee you up here, Sam, to take us away on this, because this is such an important aspect of technological change. So imagine you were given a penny and by the way, Sam, I have to admit this to you. This is a terrible thing I did. I remember saying to my son this one day, I said, hey, do you want me to give you a penny?
Okay.
And I gave him this. I said, so I'll set this up because it was kind of cruel, but he just gave me this terrible look, and I could tell what the thought bubble was saying about me. So imagine you're given a penny and begin doubling it each day. After a week, you would be receiving less than $1.50 a day, but give it one more week. Now you're getting more than $80 a day. Within a month, your allowance is more than $100 million a day. That's the power of exponential growth.
Exponential growth, right? It's not, and it's something that our brains are, we did not evolve to kind of think about these like highly nonlinear systems where things double and there's kind of this feedback. But right, exponential growth is this process of doubling and cumulative, where you're growing not by a constant amount, you're growing by a constant rate. It could be a doubling, it could be some smaller rate. And it turns out that a lot of our scientific knowledge and even our technological knowledge, and certainly we can discuss Moore's law as well in the context, they obey these kinds of doublings and these kind of like rapid growth. And so it can be, so in terms of like scientific knowledge, even like one rough proxy is just the number of scientific papers that are being published. And that obeys these kinds of growth properties. And you can look at the abilities of our, I think particle accelerators might adhere to one of these kinds of things in terms of like the kinds of things that can be done, but also, yeah, just like how what we know, right, is growing more and more rapidly. And it also goes hand in hand, going back to what I was saying with like technological growth, technological advancement also obeys this exponential kind of curve, an exponential property. And the, yeah, so like the kind of the classic example is Moore's law. So Moore's law was developed by Gordon Moore. I think this might have been before he was one of the co-founders of Intel. I can't remember exactly the timing, but it was this empirical observation that he noticed, which was he just noticed that the number of transistors on circuits, on chips, was doubling. I think initially he said maybe about every 18 months, and eventually it was modified to be about every 2 years. And he did this with 3 or 4 data points. It was some very little, very small kind of thing. And remarkably, this relationship of the number of transistors doubling has held up for a very, very long period of time, for many, many decades. And I think people have always talked about like whether or not it's going to break down, but it has held up remarkably well. And exponential growth holds across different technological techniques being used to allow this exponential curve to happen. And the interesting thing is, because each individual technology, underlying technology for memory storage or whatever it is, might eventually saturate. Rather than getting this like exponential growth, you get something called an S-curve, where it starts exponentially and then eventually saturates as we, I don't know, lose the ability to continue to advance that technology. But oftentimes, as one S-curve saturates, another S-curve kind of takes its place, as a new emerging technology takes its place. And people have looked at this kind of thing of like how to understand innovation as these series of S-curves that when they're stacked together, yield something approximating this sort of exponential growth. But it's this remarkable, yeah, this remarkable process where even though the underlying technologies might be changing, the overall like advancement of processing power, information storage, what have you, these kinds of things are actually remarkably regular. And there's a lot of discussion around why is that so? How do we get these things? And some people talk maybe it's the self-fulfilling prophecy of like, oh, because we want Moore's law to hold, we're going to just keep on trying to do these kinds of things. And maybe there's something to be that. I think also there's, to a certain degree, just the fact that as our population is growing rapidly, that often goes hand in hand with more scientists and more technologists and more engineers being able to make discoveries. And of course, that's part of this larger conversation of whether or not there is an increasing burden of knowledge and how we make discoveries. Are discoveries slowing? This is also kind of part of these just larger body of knowledge known as like scientometrics or meta-science, of like trying to actually quantitatively measure how science, the process of science and how it's done. What are the things that actually make science like easier? What makes it more likely? How do we actually get these scientific discoveries? What are the sort of the underlying properties of scientific creativity? How do we think about multiple independent discovery? This is a massive field. It's unbelievably fascinating, which is one of the reasons I wrote the book. But it's wild to see that we actually do have the capacity to quantitatively understand this thing that you would think, oh, it's so difficult to describe, like discovery and creativity are these very special processes. No, it turns out in the aggregate, there are regularities. And whether it takes the form of kind of a Moore's law of everything or this kind of exponential growth of scientific papers, there are these regular patterns to how what we know grows.
If you're working in future orientated aspects like strategy, you're able to actually use Moore's law as a map. You're able to understand exponential growth. You're able to see that, yes, this product or service that we're building might not work today, but actually will work in the future because these laws continue. They will continue the whole way. The iPod came around that way. They understood that Moore's law would actually solve the storage issue, and they actually built the whole frame, the advertising behind the iPod before it was even developed. And then they saw that Toshiba had solved the problem. They bought the patent for the Toshiba storage device. So I thought that's why it's so valuable to understand all these aspects and all these different mathematical models and scientific models, because it just helps you deal with the uncertainty or the seeming uncertainty of everything. But one thing, Sam, I'd love you to lean into a bit was you talked about the S curve and how the S curve goes from a rapid growth stage to a plateau stage. And one of the things that you pointed out was if you think of, for example, a petri dish and there's bacteria growing in that petri dish, it has a certain capacity. And I thought about the S curve as you only have a certain amount of customers for your product, or so many people will buy your product and then they turn into repeat customers. So you can't keep growing. And one of the terms that you introduced me to here was carrying capacity.
The simple way to understand it, right, is bacteria within a petri dish. When you have one bacterium that's doubling, and like I said, creates two bacteria, and then kind of 4, and then 8, and so on and so forth. At the very early stages, the doubling is the process that is kind of the most important feature. But eventually, as these bacteria double more and more, it is going to saturate that petri dish, and it's going to slow down because it turns out there is not an infinite amount of nutrients, or you're going to bump into other bacteria, or you're going to bump into just the borders of the petri dish. And so you, on the one hand, you have that very early exponential growth, but then eventually you reach carrying capacity. It kind of slows down, you saturate, and you reach these other kinds of features of the system. And you can analogize this to many different things. And so in technological advancements, it can be things around the maturity of a technology. And so like very early on, maybe when something is first being developed, there's a lot of low-hanging fruit. And so it's very easy to make this thing faster and faster or better and better. And eventually you pick all these low-hanging fruit and the development gets slower and slower. And you can also look at the same kind of thing of like, right, as a new product hits the market, every customer is going to be new, but eventually, right, you're going to slow down because you're going to run out of new customers. And like, this is, it reminds me of, was it the CEO of Netflix, Reed Hastings? He has that like famous quote of like, our biggest competitor is sleep. Like when you saturate the market, that's the kind of thing you're working on. Like you're not trying to find new customers. You're trying to compete with like a fundamental, like physiological thing. And so, yeah, like, being aware of the ways in which like an exponential can potentially break down, I think can be really valuable for understanding whether or not you're going to be bumping up against these carrying capacities or kind of the slower part of the S curve.
I always think about rabbits. So you have a population of rabbits and they're going, oh, this is great. We got a nice piece of land here. We're going to populate the land. And then it's kind of like you break a marketplace and then people kind of want to steal your lunch. But in this case, the rabbits are the lunch. And along comes a competitor like an apex predator, for example, and they go, actually, this is where we're going to settle down. There's lots of pastures here for us to feed on. And it's the same thing as the carrying capacity. They'll get to a certain size, competitor comes in, or predator in this case, and then the ecosystem changes. And I think that's a thing that we have to accept about the pace of change, is that this just happens. It's natural. It happens in every aspect of evolution. And this brings us to the pace of discovery. And I'm jumping right back here to the exponential chapter where you talked about Derek de Hoya Price. I'm probably butchering his name there. And the science of Scientometrics, because again, it was a term, and I'd love to share with our audience some of these terms just to make sense of things.
Derek de Hoya Price, he was I think by trade initially, like a historian of science. He was actually involved in kind of the Antikythera mechanism of like trying to understand this like ancient Greek gear structure that actually was involved, I think, in trying to understand certain things around like celestial behavior. But he also was, I would say widely considered like the father of Scientometrics, like this quantitative study of science. And the story goes of like one of the kind of his first discoveries was he was studying somewhere, and there was like, I think it might have been like somewhere in Singapore, the university library was under renovation. And so they gave him like a complete series of like some like scientific journal. And so he just like took the whole thing, took it home and like stacked it against the wall. And he started looking at the shape of like the height of these journals. And he found that it wasn't like this linear relationship and it wasn't flat. It actually had this very clear exponential curve. And he realized, oh, wait, science has this very clear shape. And he began then to just collect bits of information and facts about scientific discovery and scientific knowledge growth. And he realized there were these clear quantitative relationships. And it's one of these kinds of things where, yes, every single discovery has its own special story. And every discovery is special in its own way. But when you look at all of science in the aggregate, then suddenly everything goes from being fairly unpredictable to actually realizing, though, there are these clear quantitative relationships, like how what we know grows over time. Is it having these exponential growths? Are we reaching an S curve in certain developments? Can we actually try to quantify these things? And the truth is, this is also behind the underlying title of my book, The Half-Life of Facts, which is a kind of by analogy to radioactive material. If I had a single atom of some radioactive material, I can't tell you if it's going to decay in the next fraction of a second or in the next million years or whatever it is. But things change when I get a whole chunk of that radioactive material. Suddenly it goes from being entirely unpredictable to actually being quite regular. And you can actually trace out the actual half-life of how long it's going to take for half of the atoms to decay. I can't really tell you which of those atoms are going to decay, but I know that half of them are going to decay. And the same kind of thing is true with scientific knowledge, that there is this regularity when we look at science, when we take a step back and look at like the larger picture. We realize that there is this shape to how knowledge grows, how scientific discovery is being made, how the tools we use and the technologies we have can impact scientific discoveries and kind of the shape of technological tools, and even how knowledge gets overturned. There are actually regularities to that kind of thing as well.
So that was Scientometrics, but there was another term also you introduced, Eurekametrics.
Yeah, this is a term I developed along with some collaborators, I think when I was doing my postdoc, and this was actually around the quantification of scientific discovery itself and trying to see whether or not discoveries adhere to some very clear pattern in time and how that kind of relates to the difficulty of discovery over time. And I believe actually De Sola Price, he was also invited, he looked at a little bit of, I think it was going back to actually the periodic table, like looking at like the discovery of new chemical elements. And so we looked at, chemical elements, and I think certain things around like minor planets, like asteroids, and it turns out there are these kind of like quantitative relationships, and you can kind of create interesting models around, okay, based on certain assumptions of like, are we plucking the low-hanging fruit? Is all the easy stuff being discovered first? Then do we have to learn more things, and it requires more effort to actually make further discoveries? And I think there's actually a great deal of truth to that kind of thing, where and oftentimes when a field is new, the discoveries come fast and relatively easily. And then, of course, as we learn more and more, the discoveries might continue to come quite regularly, but it's not because they're of equal ease for discovery, but it's because we're exerting maybe exponentially more effort, or more scientists are involved in that field. And this is actually one of the things people have looked at, like the increased burden of knowledge, and whether it's like harder and harder to make discoveries at the frontier of knowledge, because you have to learn more and more. And similarly, it might require more and more scientists working together to actually continue to make discoveries at this kind of constant rate. And thus far, our human population, which I assume is correlated with scientific population, has been growing quite rapidly. And so therefore, science is proceeding apace. But all these different kind of aspects are features of that overall shape of discoveries themselves.
Since we've started the show, we've gone to 9 billion people on the
I don't think we've
planet.
been talking quite that long.
But actually, I wanted to talk about that because we had on the show brilliant guy, Jeffrey West. He wrote a book called Scale. I see you nodding. Yeah, brilliant book. So we did it 4 parts actually with Jeffrey on that book. It was a magnificent book. But you talked about the Santa Fe Institute, where he was the leader of that institute. But one of the reasons I bring it up is you talked about the fact that if the Earth is getting bigger, and cities in particular are getting bigger, there's more collaboration, and as a result of more collaboration, there's more science, there's more breakthroughs as a result of that. I'd love you to share your thoughts on that, because I thought this was really important, Sam. I wrote an article a few years ago, and it was after COVID, where people started to work from home, and it was WFH, work from home. What did I say? DFI, disastrous for innovation. And what I was getting at was that the lack of collaboration, bashing out ideas, disagreeing when it needs to happen respectfully, all this kind of stuff, that it's very difficult to do that on a call like this, even depending on if people are working on that independently and then sharing their knowledge together. But it's much easier to do as a team, where you're bringing all these different people with their different backgrounds, different neurodiversity together in order to collaborate. And I thought it was really interesting. You said a group of researchers at Harvard Medical School looked at tens of thousands of articles published by its scientists and mapped out buildings on campus where they worked. And through that work, they were able to look at the effect of distance on collaboration. And they have found exactly what they had assumed, but no one had ever measured, which was the closer two people are, the higher the impact of the research that results from their collaboration. And they found that just by being in the same building as your collaborator, it actually makes your work better.
Right. Like distance, even down to the level of the building, can have that kind of impact on the combinatorial aspects of collaboration, or the serendipitous kind of connections, or just the ability to share and exchange ideas in some sort of productive way. I think that's, super interesting. And it mirrors many of the kinds of things that Jeffrey West and his collaborators have studied, which is this idea that there are these increasing returns to scale, that when cities get bigger, they're not just generating more innovation and more ideas. They're actually generating more innovation and ideas per person. There's the kind of this super linear relationship. And I think like we have to take into account kind of the geographic aspect of this kind of thing. I'm of a complicated mind about working from home and the ability to collaborate across distance, because I actually think when it comes to collaboration, there are ways of overcoming distance. And certainly one of the other interesting things, though, is certainly when it comes to scientific innovation, kind of other kinds of innovation, there's also increasing returns to like intellectual diversity. And presumably, the more distant you are, you might be exposed to very wildly different ideas. Now, geography versus intellectual distance, that could be an open question. You could be very far apart and still be exposed to the exact same kinds of ideas. But I do think that maybe there's this interesting interplay. On the one hand, you want to be geographically proximate to have rapid exchange of ideas, but you also want to be intellectually distant, because then you're going to be exposed to different domains. And if you can productively overcome jargon barriers and things, really allow you to do this kind of like combinatorial recombination kind of thing that we've been talking about, of like combining things from different domains together. So I think it's a complicated dance there of how we can do those kinds of things. But I do think that trying to understand what are the determinants of creativity and discovery, whether it's factors of geography, whether it's certain things around people coming together from different areas. And so I think there was research done a number of years ago looking at patents that arose from like very different disciplines or technical domains. I'm not sure I'm going to remember this entirely correctly, but it was something to the effect of that the more varied the domains, or where the people were coming from who were involved in these kinds of things, the lower the average impact of that kind of patent or that kind of work, but the higher the variance. And so oftentimes when you're coming from different areas, it's actually really hard sometimes to make useful collaborations, because you may be talking past each other, you don't really know what you're talking about. But when it does work, it can have this high variance. It can be really valuable and really impactful. And so I think just trying to understand what are the features of creativity and novel discovery, and how those things can be balanced together, is something that, we need from the world of metascience and scientometrics. And I just want there to be more research into this kind of thing.
Serendipitously, when I was researching your book, I was reading parts of Everett Rogers' book, The Diffusion of Innovations, and he talked about people he called cosmopolites or cosmopolites. And these were people who traveled widely or read eclectically and read widely, more broad than deep. And I thought about how, to your point there, it's that necessity. So I like working on my own. I like like going to my cave, and
Likewise.
going to my library and just studying. But what I think is that it's the collaboration or the conversations. I'm very lucky I have conversations like this, but very few people get to have those conversations, because they are so busy or so focused on a target. And I think in doing that, you miss subtleties of a conversation, the throwaway comments, the water cooler moments. That is difficult to reproduce unless you're a certain type of person. And what I mean is, if you have more forum type conversations where people can discuss and beat up ideas, etc., after they come out of their cave, that you can just miss the collaboration. And I'm setting us up here for a very interesting story you tell in the book about the collapse of essentially the bridge that connected Tasmania to Australia and what happened as a consequence of that collapse.
I love this idea of needing these kinds of collaboration interactions among people. And the story that you're mentioning is there used to be this land bridge between Australia and then Tasmania. And when it vanished, there was a much smaller population remaining in Tasmania. And as a result, not only did, so it was a smaller population relative to Australia, knowledge was actually lost, where it was because the population was so small. Not only could there not be, I guess there couldn't be specialization, but there also couldn't be the collaborative power of not only not building new technologies, but actually certain technologies can no longer be preserved because there wasn't in that population the critical mass required to preserve that kind of thing, as opposed to, as compared to the technological complexity on the mainland of Australia. And I think the researcher who was involved in this also just kind of correlated it with the size of populations and the sizes of landmass in general, which showing that like the larger population you have that is productively interacting, the more advances in innovation that can be happening. But I would say one thing, and actually I didn't mention this, I don't believe I mentioned this research in my book, is that we often, certainly within science, we don't necessarily optimize or incentivize certain of those kinds of connective kind of tissue roles. And so there's some really interesting research that came out maybe 10, 15 years ago or so, where it was looking at the productivity, I think it was like 50 years worth of like immunologists. And it was looking to see which researchers were like the most highly cited, but they also looked at, in terms of like their papers being referenced by other papers, but they also looked to see which researchers were more highly acknowledged at the end of the papers. And so it was like at the end of a paper, in addition, you just say like, oh, thanks to these following people who kind of like helped me with like conversations or whatever it was. And they looked at this one category of people who had a mediocre level of citation. So they wouldn't necessarily be considered top-notch, like superstar scientists, but they had a very high level of acknowledgement. And it turns out when those people died, the productivity of all of their collaborators actually dropped. And so it showed that these people were actually really valuable for that scientific process of like maybe sharing ideas or connecting different kinds of bits of information together. And we need them. And there's a whole larger question of, okay, how do we incentivize this in science? But I think this idea that we have to recognize that there is this much less tangible or maybe less easily measured kind of thing. There is this role of like, when you have a large population, if it's all siloed or if people are siloed, that doesn't matter. It is the cross connections and the cross pollination of ideas that is really, really valuable. And one of the stories actually I mentioned in my book is related to, I think when I was a postdoctoral fellow, and a friend of mine, we were working on a paper and we had to find some sort of statistical metric for clustering of data or whatever it was. And we couldn't figure it out. We were searching for things online, couldn't find any answers. And we're like, okay, we'll just make up some measure. It's not going to be great, but whatever. And I was like, oh, why don't we just talk to the statistician down the hall? We went to him, and I feel like within under a minute, he gave us the exact answer we needed. And it was because he was very smart and really good at statistics, but he also was able to fulfill that role of being that kind of connective tissue. And he was also able to overcome jargon barriers because we didn't even know the kind of terms we should even look for. And I think that's one of these things where we think, oh, all this knowledge is out there. We should be able to stitch together bits of information. This should be this golden age of scientific discovery and innovation. And in some ways it is. But even though everything is out there, if you don't even know the terms to look for, it's going to remain, going back to like undiscovered public knowledge, it's just going to remain fallow. It's going to be there and be hidden. And so there is still, and maybe with AI, this will change, like maybe the AI will fulfill this role, but there still very much is a role for people or tools that can act as this connective tissue to allow the population as a whole to allow innovation to move forward.
this is what I was getting at with the people working together, but it's more than physical proximity. It's the willingness for that colleague to give you the time and not to see you as a competitor and why should I help you kind of thing, which can sneak into academic organizations, unfortunately, and scientific, and every organization where there's more competition within than there is to the outside world. And the reason I mention that is I loved the study that you shared about Nobel laureates, where when they were more of a mensch, they actually were more successful. It was linked to scientific productivity. To set you up here, you give the example in the 1960s of a lady called Harriet Zuckerman, a sociologist of science, which is somebody who studies the interactions and people underlying the entire scientific ventures. And she decided to study the scientific output of Nobel laureates to see if any patterns could be seen in how they work that might distinguish them from their less successful peers. I'd love you to share the output of this. It was a brilliant one.
I believe what they did was they looked at the position of authorship in papers, because oftentimes, I think within the literature, and of course it varies from field to field, it's like the most central person involved was the first author. And it was one of these things where I think she found that these, it might have actually been eventual Nobel laureates, like fairly early on in the career, they gave kind of pride of place to their younger collaborators. They let them be the first author very early on. And it was kind of this very sort of, kind of mensch-like approach of I like generosity of spirit. I want to kind of allow other people to be successful. And it turns out that there was a correlation of that willingness to give up the first authorship was actually correlated to massive productivity. And it's these Nobel laureates were, some of these people who were actually very, very giving and willing to not just take all the glory for themselves, but allow their students or other researchers they were collaborating with to also share in that success. And that actually was a really, really important feature. And I think that, going back to what we're saying of certain things we incentivize in science, of making all these discoveries and making discoveries by yourself. But the truth is, science and all of innovation is this highly collaborative effort. And it's very team oriented. And actually, there's been a lot of research in recent years around the nature of team science and what are the kinds of teams and the makeup of teams. But there also needs to be this understanding that if it's a team sport, then you actually need to really think of it as a team sport. You all rise and fall together, and how you think about that kind of thing is very important. And making sure that other people can be apprenticed and mentored and share in that success so that they can become even more successful. And then they will create their own lab and I guess actually mimic that same kind of behavior. And so those kinds of things are really, really important.
Yeah, and having played in sports and teams, I have played in teams where some of the best players are playing for themselves and the team never does well as a result of that. They're just playing for their own personal glory, which came to mind when I read this. I thought we'd finish, Samuel, on the asymptote of truth, and maybe you'll explain that term asymptote as well for those who don't know it. But I have a little quote here, and I love this. This was probably one of my favorite stories, along with the dinosaur story. You said that anyone who was alive during the late Cretaceous between about 100 million and 65 million years ago, I don't think there's many of them listening to the show, would have seen many familiar creatures such as the fearsome Tyrannosaurus, the duck-billed hadrosaurs, numerous birds, and even a selection of small mammals. But if you ventured into the sea, you would have seen a wide variety of marine creatures. Among these animals was what's called a coelacanth, a grey, thick-lipped fish. They were one of the most hideous creatures of this period, Sam tells us. And the coelacanth is an example of what's known as a Lazarus taxa, living things that are presumed long extinct until contrary evidence is discovered. Seems like there's not a lot of them. Turns out Sam's going to tell us a different story.
Yeah, the coelacanth, it's this weird, ugly fish. I imagine it's attractive to other coelacanths. But it was presumed extinct people thought, it was extinct for tens of millions of years until I think about 100 years ago or so, where someone caught a coelacanth and realized, oh wait, this thing that people thought was long extinct was actually still alive. And it was one of these fish or one of these creatures that presumably it was very well adapted to its specific niche. And it did not need to change over time or evolution. And it stayed there, but it was just not known to people that it was still actually alive. And right, these Lazarus taxa, these taxa that people thought were extinct, but actually have been effectively resurrected because we now discover living versions of them, is actually not entirely a rare thing. And so there was some research where someone looked at a number of different animals that had been thought to be extinct at some point, and I think they found like a third of them had actually been rediscovered and were found actually to still be extant. They were still alive. And it shows this larger idea that we are slowly but surely approaching a true understanding of the world, sometimes by discovering things that we thought were extinct are now actually still alive. But this is this idea of the asymptote, which is like in a graph, you might never approach a certain value, but you're slowly but surely getting ever closer and ever closer. And so it's like you're asymptotically getting closer and closer to this kind of thing. And the way to think about this in terms of knowledge, again, is we're not just constantly overturning everything we thought we knew. We are slowly but surely, asymptotically, getting closer and closer to a true version of the world. And the way to think about this is there's a great quote by the science fiction writer Isaac Asimov that I mentioned in the book, where he received from a reader a letter saying like, oh, we thought the Earth was flat at one point and we were wrong. We thought the Earth was a perfect sphere, but then it turned out it was actually an oblate spheroid. Like we were also wrong. Like, how can we know anything? And Isaac Asimov's response is basically like, if you think that thinking the Earth is flat is just as wrong as thinking the Earth is a perfect sphere, then your view is wronger than both of them put together. And it's this idea, like, and it turns out you can actually measure the amount of error of believing the Earth is flat versus like to what we actually have versus believing it's like perfectly spherical versus an oblate spheroid. And we are slowly but surely removing a certain amount of error. And so even though these views seem wildly different, overall, we are approaching ideally a more complete version of what the world is. Now, of course, and I imagine every generation has thought that like we've known it all and now the rest is just like rooting out a few little errors. And of course, we're going to discover things that we thought we were true are actually quite different from the way the world is. And for me, that's very exciting. But I do think slowly but steadily, we actually do have a really good understanding of the world, and we are asymptotically approaching, hopefully, a true understanding of reality.
Beautiful. And I loved what you said. This is my final little quote for today. And then I'm going to come to you, Sam, and ask where people can find you and reach out more. And don't forget, we have more from Sam as well. I'll show the other books now in a moment. You said here, this sort of large-scale analysis is not just for understanding the nature of a Lazarus taxa. It can be extended more generally to enable us to understand the entire edifice of science and all education, we might argue, and how we overturn long-held scientific beliefs. By looking at how science changes overall, we can see the patterns in how scientific knowledge is revised, and it can lead us to measuring the half-life of facts. Beautiful. Nice cherry on top from me today, Sam. Maybe we'll come to you to share where people can find out more about you, your work, your writing, etc.
So my website is arbesman.net, so just my last name, .net. I have a newsletter you can subscribe to there. I think it's at arbesman.substack.com. And and then you can find a whole links to selections of my writing, my books as well. And I've written 3, and it sounds like we're going to be discussing more of them. But so arbesman.net and my newsletter as well. Those are the places to find me online.
Absolutely brilliant. So that was the half-life of facts. Let's put that one back on the shelf. I can feel like I've moved a little bit towards more knowledge today. And next up, we're going to have this book, Sam's second book, Overcomplicated. That's going to be our next book next week. And then we're going to move to his latest book, just released, which is The Magic of Code as well. And Sam, I'll share all the links of where to find you, Substack, etc., for those people who are interested in finding out more. And just final word for me is to thank you, the author of Half-Life of Facts, Samuel Arbesman. Thank you for joining us.
Thank you so much. This is so much fun.
Thanks as always to our sponsor, Kyndryl, with a unique blend of AI-powered consulting built on unmatched managed service capability. Kyndryl helps leaders harness the power of technology for smarter decisions, faster innovation, and a lasting competitive edge. You can find Kyndryl at KYNDRYL, Kyndryl.com.